This is the GIS lecture for Chapter 2, Mapping GIS Data, from the 5th edition of our textbook, which is titled Mastering ArcGIS by Mary Beth Price. These slides were created by Mary Beth Price and are subject to her copyright as shown in the bottom left-hand corner. Since this presentation was created by Mary Beth, it is not exactly what is needed in our course, so I will skip over some slides and discuss slides in further detail as necessary based on our objectives and goals of the course. In this chapter, we're talking about ways to map data. Another item I should mention is if you'd like to copy down some things that you see on this slide or to read further, feel free to press the pause button and you'll be able to pause and look at your screen. You may also create screenshots using Jing or Alt Print Screen, of course, to put into your notes. And again, this is to supplement your reading of the book, not to replace it. Map types and data types. There are single symbol maps, unique value maps, quantities maps with graduated color, graduated symbol, and dot density. And for those maps, we use nominal data, categorical data, ordinal data, and interval and ratio data. What is nominal data? Nominal data can be summarized as names or uniquely identifiable objects, such as Washington State, or owners of a parcel, tax ID number, parcel ID number. Each feature will have its own value, such as Washington, Idaho, and Oregon shown in this image. And they are usually portrayed on the map as labels. Single symbol maps display all features with the same symbol, and they combine with labels to portray nominal data, such as the stars that are shown on this map, or the rivers that are shown on this map. Categorical data. This places features into a defined number of distinct categories. Category names may be text or numeric, and they are portrayed by different symbols for each category. For example, the wells by type. There are 5 of those listed there. Road class, there are 6 different road classes listed there. And land use. And notice the colors for land use are not varying of one color, they are distinct colors. Albeit in this example they are not too distinct, or perhaps not distinct enough. They are distinct. They shouldn't be shades of the same color. Unique value maps. This is where a different symbol is used for each category or value, such as volcano types, or road types, or geologic units. Ordinal data. It's a type of categorical data. It ranks categories along an arbitrary scale, such as low, medium, and high slope, village, town, city, grades, A, B, C, D, and F, rank of the best city to live, 1, 2, 3, etc. They are portrayed as categories, but choosing variation in symbol size or color is done to show an increase and or decrease. And notice here we have the shades of color in the example map. Interval or ratio data. Interval data places values along a regular numeric scale. It supports addition and subtraction, and some examples are temperature, pH values, and elevation. Ratio data places values along a regular scale with a meaningful 0 point. This supports addition, subtraction, multiplication, and division. This is examples such as population, rainfall, and median rent. The meaningful 0 point talks about how if you have a population of 0, it's 0, none. If you have 0 rainfall, there is none. And same with median rent. If your rent is 0, you're not paying anything. Whereas with temperature, a temperature of 0 degrees, there's still a temperature there in it. It's 0, and that 0 represents something. The same with pH, and the same with elevation. If you have an elevation of 0, that's known as sea level, and it's not a meaningful point per se. In mapping numeric data, interval and ratio data must be divided into classes before mapping. They're mapped using variations in symbol size, thickness, or hue. And in this case, we're looking at cities with varying symbol size, roads with varying road line size, and yearly participation in varying hues of color. We would not use a green, yellow, darker yellow, and red for precipitation and rainfall. It makes more sense to use differing variations in the hue. Classed maps. On the left, we have a graduated color map, which is a choropleth map. On the right, we have a graduated symbol map with different size symbols. They're similar, just different ways of going about the same process. Colors for choropleth maps generally use a change in saturation or close hues to indicate an increase. And you should avoid using too many colors, which tend to mask an increase. Normalizing classed maps. If the size of the sample impacts the measured value, then data should be normalized. By percent of total, for example, percent of farms in each state, or the percent of mobile homes in each state. Or by another field, farms divided by area, or mobile homes divided by the total housing units. Unclassed maps. Here we have a proportional symbol map and a dot density map. And these are just proportional symbols on the left to show the amount of population, and then on the right they show one dot equals a population of 100,000. And these dots, you must be aware of, are located randomly within the shape. You could exclude them from certain areas, but we'll talk about that at a later time. Symbol psychology. Where is there less rain, or which towns have more people? What do you notice from this map? If you're thinking the bigger circles mean more people, you're probably right. If you're thinking the browner parts are less rain, then that's symbol psychology. More symbol psychology. What's there? If you see a plus or a rectangle with a flag on it, it may mean something to you. In this, on the bottom right, where's the danger? Automatically, you're most likely thinking the danger is in the red areas. And where's the water? In this case, it may be deceiving to somebody who doesn't know the geography. However, for us, we notice that actually the tan area is the water, and this is a bad example of where the using color, because where's the water? The water is actually where the tan is. Let's move on to a little bit about displaying rasters, even though we'll cover rasters in another chapter in full detail. Raster types. They're discrete data, as shown over here, represent discrete objects such as lines or polygons, takes on relatively few values. Adjacent cells often have the same values, so all of the cells in here are 14, all of them in here are 13, all of these are 9. And values may change abruptly at boundaries. There's a distinct boundary in these rasters. Whereas continuous data, there's thousands or millions of potential values, and very few adjacent cells have the same values. Values may change rapidly from cell to cell. Raster types. Thematic rasters. Certain quantities that represent map data, such as land use or rainfall, may be continuous or discrete. Image rasters contain satellite or air photo data, generally represent brightness, and they're usually continuous. This would be more of an image file. Displaying thematic rasters. We have categorical and ordinal data, unique values, discrete color. Interval and ratio data, we have an example of classified, where there's distinct breaks in the data. Therefore, it's a little bit choppier in the display, which may be useful at times. Or stretched, where there's very fine detail between each individual cell. You can definitely notice the difference between classified and stretched. Slicing. Slicing is discussed in the book. It's a little bit easier to understand than just reading this, but slicing divides it up into 256 colors. And you're better off reading the book for a better description of that. In this slide, we're looking at a raster with a lot of different colors being spread out to 0 to 255, which gives us 256 colors. Sometimes this needs to be done for display to work properly. Stretching. After slicing, stretching enhances the display by removing less common values at the tails. This data to the left is eliminated, this data to the right is somewhat eliminated, and it's put back to 256 colors, or 0 to 255. Image display. On the left is a single band image. On the right is a 3-band composite image. The image values represent brightness as a 0 to 255 DN scale, and DN stands for digital numbers. If you notice down here in my notes, I have images may have one band or multiple band. Each band contains values from 0 to 255. Let me stretch this up for you to see. A Landsat TM satellite image contains 7 band, one each corresponding to a different range of wavelengths measured by the instrument. The first 3 bands correspond to blue, green, and red. There are also near-infrared, mid-infrared, and thermal bands. And that'll be talked about more in a remote sensing course. Stretching images, similar to what we saw before, stretching it out to the full scale. And an example here is no stretch. Most of the colors are in the middle gray area. And stretched out, a standard deviation stretch makes it more viewable. It maximizes brightness and contrast, and there are different stretches: minimum, maximum, standard deviation, equalize. It's a little bit beyond this course, but it's good to know a little bit about what they're talking about. Here's some more effects of stretching: min, max, stretch, standard deviation. Shows you the differences, what you can do. And often it's a case of trying one, trying another one, and determining which works best for your situation. RGB color composites. These are 3 different image bands, red, green, and blue, and put together for a composite color image. Landsat band, this would be true color 321 RGB, false color 431, and other 741. And it's bands 1 to 7 represent different wavelengths of light. And until you get into remote sensing, we'll leave this at that. Index colored rasters. Common for scanned maps, more efficient way to store colors for scanned rasters than RGB bands. Each color on the map is indexed to a special unique value palette, and you can modify the color choices individually. And in this case, it may be a code that represents each of the items over here. For example, 6 looks like it most likely represents a certain type of building. 0 is a common node data value, and we'll notice right here that there's black in the visual, whereas over here it's listed as clear or transparent, or in some cases white. We have some more notes down here. Images and grids often contain areas where values are unknown. Usually these are stored as special data value called node data. And we'll leave that as it is for now. Transparency. Well, here there's a transparency of 0, but you can see when we overlay these two items, we can see some of the colors from this image on top of the hill shade. So it adds a little bit of a varying view if you'd like to do so. We're now going to go into classifying numeric data. Classifying data. This image is in your textbook. It shows the Jenks natural breaks, which is an option, equal interval, defined interval, quantile, geometric interval, and standard deviation. These apply to both vector and raster maps. Different classification methods are available. The choice impacts the map appearance and validity, and the best method depends on the data distribution and the objective of the map. And those are some decisions that you're going to have to make as you build your maps. Sometimes they'll be provided, sometimes you'll have to make your own decisions. Going to quickly run through this slide. Just pass over it, actually, I should say. These are some common data distributions. This is known as a normal curve, a normal bell curve, and then there's 3 others that they're showing there, but we won't get into that. Natural breaks, Jenks, as it's called in GIS. It exploits natural gaps in the data, good for unevenly distributed or skewed data. It's a default method, and it works well for most data sets. You notice where the gaps are, that's where they apply the breaks. And breaks means breaks within the data, breaks between the color values. Equal interval, we specify the number of classes and divide it into equally spaced classes. It works best for uniformly distributed data. Defined interval, the user chooses the class size and the data determines the number of classes. For here, we have an interval size of what looks like 10 million. And then from each color has 10 million, and the data is divided up. It works best for, again, uniformly distributed data. Quantile, the same number of features in each class. You may get very unevenly spaced class ranges, and the results depend on the data distribution. And again, sometimes it's a matter of what works best for your situation. Geometric interval multiplies each succeeding class boundary by a constant. It works well for normal or skewed distributions. Standard deviation shows the deviation from the mean. User chooses the units, for example 0.5 standard deviations, and assumes data are normally distributed. And that is beyond this course, but as you progress further, you may be more interested in using these standard deviation breaks. Mapping GIS data. Map documents and data frames. So now we're going from the theoretical of what we're talking about and going to actually the data frames where we build the maps. The map document. Map document stores a collection of data for viewing and analysis, and one or more data frames. This example has one data frame that we can see. It says hazards. And it stores properties for each layer, the symbols, etc. And it stores a page layout for printing. And the layout tab is located right there where that tip of the arrow is. That's what you need to produce your layout, which is shown right here. It stores references to files, but not the actual data. These are paths to the data, which is why without the data, this map would come up blank. And we'll get into that further. Map documents and data files. The data, these items over here point to the data. In this case, all of these will point to their data. The same document or the same data can be used by many map documents. Edits made in one document appear in all. Shipping map document without its data is useless, which is why we must always include our data and why we keep our data very well managed. And changing locations of the document or the data can cause huge problems, catastrophic problems, in that the map will not draw. Data sources for layers. This is how we can see what our data is. It's listed on the source tab and it's stored as a path name. And here the path name is in the Microsoft US Data MDB, which is the Microsoft database, which is a personal geodatabase. And it also shows on the source tab the projected coordinate system and the projection used by this data. Path names. Sources are stored using path names. And in this case, if we have a state, city, or county, it may be in the USA folder, in the GIS data, in the C folder. The ... over here means go up one level. Broken data links occur when a map document cannot find data using the stored path name. And let's go up here to the blue. Absolute paths always start at the top of the data tree. Relative paths start at the location of the map document, which is why we normally want to use relative path names. Broken data links. These occur when a map document cannot find data using the stored path name because A, the data was removed or deleted, the drive is not available, the map document copied to a different computer, or the data is not sent with the map. This is what it looks like. It comes up with an exclamation point and you cannot find your data. You can fix it, which is what we've done in the class. You would right click data, repair data source, or over here you can set data source. I don't normally use this method down here. Normally it's right click data, repair data source. When do we use absolute paths? When data is placed on a central server for access by many, data will not be moved nor rearranged. You want to be able to transfer map documents without transferring data. We can just put a big X on this one because we always want to use relative paths. When you plan to keep data with its map document and move them together as a set. And when you want to distribute maps and data to other organizations, you send the data with the map. Here's a quick overview of what ArcMap looks like. You've used this. We have a data frame. We have layers. Notice these are not shape files now. These are actually layers. They link back to shape files, but these are not shape files themselves. These are layers. We have another data frame, and over here we have two data frames. You can tell the active data frame by the dots around it, or the dashes. This is how we'd locate two maps on one page, or use an inset map or a reference map. Data frame properties. You right click and go to properties to get the data frame properties, and in there are 10 tabs. We'll be exploring all of those tabs throughout this course. Adding data to frames. We've already done this. You connect to a folder, and then you start to select your data. Connecting to a folder just creates a link to a specific folder. Sometimes you'll go right to Austin. Sometimes you'll go just to the main folder, the data folder. There's benefits of doing it both ways. There's a little note down here. Adding data means loading data in layers tables into the ArcMap for display and analysis. All data files are located the same way. You know all that. Layers in ArcMap. They refer to a spatial data file. They are not technically a spatial data file. They refer to it. They do, however, store properties. For example, over here we have two different versions of counties. I believe this is Oregon. They're both referring to the same data set, but they're symbolized differently, and that's why they're considered layers. They store properties, and it's held in memory and saved with the map document. And they may be saved as a file. Layers for display. Again, we have vegetation up top, and we have vegetation down below. It's the same shapefile with different symbols. You can symbolize it using different aspects of the file. Here it's crown cov, here it's cover type. Layers for storing properties. Store symbols, labels, and display settings for single or groups of the feature classes and open them in new map documents quickly. So here it's saved as a layer, usmap.layer. Using ArcMap, getting into even more technical. We have a menu bar up top, the map scale, the data frames we already talked about, the active frame, you should be able to tell it's the one on the bottom. Page units display, we don't use that often, but it could be valuable. Data layout view is right there. It's pointing to the wrong spot. Right there is layout, right there is data. Toolbars and windows. These are docked windows. This is a unique setup. I've not seen that before. When you grab a item such as this and drag it, these little items will light up and you can dock your windows. It just takes a little bit of practice and you can get it to stick wherever you want. This one's a floating window. This one's a floating toolbar. This one's a window tab, which you can pin right there. And you can practice that on your own. Catalog window. Almost always have this showing when you're in Arc Catalog, and you have access to most Arc Catalog functions within ArcMap, and that can be pinned or pushed back into ArcMap. Here we have a view mode, we have a data view, and we have a layout view. This is how you make a map. This is how you do your analysis. Table of contents views. We've learned this already. List by drawing order, which is the first tab. List by source, which is the second. List by visibility. Don't normally use this one. List by selection. I don't usually use that one either. Normally it's drawing order or list by source. In drawing order, you may click and drag layers above and below each other. In list by source, you may not. Layer control. Here's where we can go to properties. You right click on it and go to properties, and you have layer properties. Then this is where we symbolize. Finding features, you could use the find tool, which looks like a pair of binoculars. You'll do that in the labs. The measure tool, you can set the different types of areas that you'd like, or distance, miles, etc. Here it's actually looks like they're saying, oh, it is saying area in feet or acres, etc. And then there's distance in kilometers, meters, miles, etc. Dynamic labels. This is a great feature of ArcMap. The dynamic labels have one of the layer's properties. They turn on and off for entire layers. They're redrawn each time the map view changes, and they use auto placement to ensure no overlap between labels, or at least they try to create no overlap. And it may change between the screen and printing. Label properties. Here we have placement properties to help tell ArcMap what to hide and what not, or what has higher priority over the other. In this instance, this looks daunting at first, but it tells you the preferred top right, everything is allowed, and then it tells you the highest important places down to the least, with being 3. And it's most often easier to play with that, but let me bring up the text below. It's actually quite a bit. The label placement options help manage the overlap and optimization of the labels to give you the best possible result. And you can read that in the textbook. It's verbatim out of the textbook, I just realized. Some more placement options: always horizontal, always straight, or try horizontal then straight, and that's a mix of the two that are above it. Line placement: horizontal, parallel, curved. Curved is usually good for rivers because rivers do vary and it appears to look better. These are not good for rivers, just horizontal. Parallel sometimes works, but curved is usually the best for rivers. Make a mental note. Scale range. This helps to unclutter your map. You set the scale range so that some labels appear at only certain levels of zoomness. For example, don't show labels when zoomed out beyond 1 million. And then, or in beyond is the maximum scale. And that's best learned by practicing and trying it out. The labeling toolbar, might get to that in this lab. It helps to create, specifically when you have a lot of labels, to create reference maps, etc. And doing or practicing with this is the easiest way to get used to it. Let's talk about symbolizing features, which is a task you'll do with almost every map. You have to assign symbols to points, lines, and polygons. You can choose from available symbols and edit their properties to get the desired result. Selecting and changing symbols, we have points, lines, and polygons shown, and this little button right here, Edit Symbol, provides a plethora of different options. You are not stuck with just what you see in the general windows. The symbol selector, you can go to style references even, and then you get even more sets of different styles. And you will be practicing with some of those throughout the labs. Here are some more styles. There's a forestry style, utility style, Esri style is the one that's usually loaded first. They group common symbols together. They share a common theme or purpose and be saved, copied, and shared. Editing symbols. This is where you go into the Edit Symbol button and you can modify them drastically. You can, for example, here it added a blue circle beneath the plane. And that's just a minor change that you can do. But there's many other options for editing symbols. Map types: single symbol maps, unique value maps, quantities maps, graduated color, graduated symbol, or dot density. There are chart maps, multiple attribute maps, and that's done within the symbolization tab. Data type and map type. And this is a good slide to save. You may want to create a screenshot. Depending on your data, this column, that dictates what kind of map you create. And I just moved that by accident. There we go. It's back to normal. And take a screenshot, pause the video if you'd like, and make a copy of that. Making a single symbol map is easy. Just go to Symbology in the Layer Properties, click Single Symbol, and you can create your symbol map. Unique Values map. Go to Categories, choose your field, add values or add all values, and then make modifications from there. Making a graduated colored map, you go to Quantities, choose graduated colors, symbols, proportional symbols, or dot density. You add a value, perhaps you add normalization. You make infinite number of modifications in this box, and then you'd press apply, take a look, and if you like it, you click OK. Normalizing data. I just brought that up again in the last slide. Normalizing data is usually good when you're determining things such as the amount of farmland or the farm numbers. Another one is population. You want to know population density, or you want to know the number of people living in poverty out of the total population. You can use the symbolization tab in the layer properties to do that for you. Graduated line symbol map to show, I believe these are highways. It could be rivers. In fact, it's probably rivers because of where they're originating. But either way, it looks like miles. So based on the miles, there's no normalization. Oh, population served by highways. So there it is. It is roads. Classifying data. We already went over this slide. Classifying data using manual breaks. We did not discuss this, but you can change it to manual. You would click here on one of them and start changing the breaks. Excluding data from classification. This is the data exclusion, and you would pull in, for example, median age equals 99. I'm not exactly sure what they're referring to here, but you can exclude data from the classification if it's beneficial for your project. Symbolizing rasters. We'll have a few more slides before wrapping up. This again is covered in chapter 8, but let's take a look. Unique values. And here unique values uses a 32 color shade set. It assigns a unique color to each cell with the same value. And there would be 32 colors in this example. Discrete color uses 32 shade set, assigns a unique color to each cell with the same value, and there's no control over individual colors. Whereas with unique values, there is control. You can set your color value. Moving on to a classified raster. Here we have a classified raster. We've got an interesting color ramp that shows most likely snow going down to water. We have mountains, vegetation, perhaps sand. At least that's what it's looking like from here. A stretched raster is a little bit different. There's 256 colors, and you can modify things such as invert if needed because of your data, and there's an infinite number of possibilities in here. It's probably beyond the scope of this class. And A symbol image band display. We looked at these a little bit earlier, but this is where you would set it. You'd go to the stretched and apply your settings. And then a multi-band image display. This would be a RGB composite. And you make your settings in here. And most of the time in this course, you'll be provided with inputs, although it would be to your advantage to try different values to see what other values do to your data. This wraps up chapter 2, and again, if you'd like to make screenshots, feel free to go back, pause the video, take screenshots, and put them in your notes. Stay tuned for chapter 3.